Welcome to this lecture. This is the first lecture of week 8. In this lecture, we are going to study some important structural properties of measures. Using these results and consolidating whatever we have learned throughout this course, later in the week, we are going to make some very interesting comments. In particular, as promised, in a later lecture, we are going to finally talk about absolutely continuous random variables and their expectation. In particular, we are going to see that as seen for the case of discrete random variables, the usual formulations that you have seen in your basic probability theory agrees with the measure theoretic structure. But all of these are now coming under the umbrella of measure theoretic structures, and this is a very general framework now. Okay, so let's move ahead and discuss the structural properties of measures. So in this lecture, we are going to focus on certain results which are usually referred to as decomposition of measures, and using these results, later on we are going to talk about absolutely continuous random variables and their expectations. So before proceeding, let us first fix the notation. So for us, we will work with measure mu on some measurable space omega script f. So omega script f mu will construct a measure space. Now let's first recall this result from week 6, that given any non-negative and measurable function small f, if you fix the measure mu and fix that measurable function f, but vary the sets over which this integration is being conducted, you are going to get back a measure, right? And we have also remarked earlier that there are some special cases where if you are dealing with f to be integrable, so that integration of mod f is nothing but integration of f which is finite. So f is given to be non-negative, so mod f equals f. So integration of mod f equals integration of f itself, and if f is integrable, these integrations are finite. But this is the total mass associated to the set omega under the measure nu, right? So therefore this nu becomes a finite measure under this condition that f is integrable with respect to the measure mu, right? So here integrability refers to the original measure. And moreover, you can also make this statement that for a general non-negative measurable function, you expect to get a measure nu to be sigma finite, provided your given measure mu is sigma finite, right? So you have these structures for such new set function. Great. But also consider this more general case, that if you are dealing with a measurable function now you can take positive or negative values, but if you assume that this is mu integrable, so that is as per definition, integrations of f plus and f minus both should be finite. Then separately f plus and f minus are non-negative measurable functions, and therefore you can talk about this new set functions which we write as nu plus and nu minus. So what are these? So you have fixed the function f. So f plus and f minus, these functions are also fixed. They are non-negative and integrable. Now if you work with different sets coming from your domain side sigma field, you are going to construct these set functions nu plus and nu minus. So these are just integrating these non-negative functions f plus and f minus, which are also integrable. So as mentioned earlier, these will be finite measures. But recall earlier that we had mentioned that these functions f plus and f minus cannot be simultaneously positive at a point. So the set of points omega such that f plus takes positive values and f minus takes positive values, that set is an empty set. So this was mentioned in note 17 of week 3. So therefore you observe that nu plus, which is defined in terms of the function f plus, that will be 0 if you are working with sets where f minus is strictly positive, right? So there f plus must be 0. On the other hand, if your set capital A is contained in the set f plus being positive, so there the function f minus is 0. So therefore if you integrate there, nu minus will give you the value 0, right? So that's what it happens, that you get these two distinct sets, disjoint sets, where you get these measures are providing masses separately. Correct? So with this observation, we now make this definition of mutually singular measures. So what is the definition? That you take two measures, mu1 and mu2, on the same measurable space. You say that mu1 is singular with respect to mu2, or mu2 is singular with respect to mu1, or mu1 and mu2 are mutually singular. So all these three terminologies are the same. So you can refer to mu1 being singular with respect to mu2, or you can say mu2 is singular with respect to mu1, or just to be very clear, you can just say mu1 and mu2 are mutually singular. So all of these mean the same thing, and that is defined as follows, that you can find some set in your sigma field such that mu1 associates 0 mass to that set, but mu2 associates 0 mass to its complement. So it's as if you are dividing the whole domain omega into two parts, A and A complement. On the first part, mu1 assigns 0 mass, so mu1 is essentially focusing on A complement part. Mu2 assigns 0 mass to A complement, so essentially mu2 is concentrating its attention on the first part A. Okay, so therefore if you get any subsets of capital A, there mu1 will associate 0 mass. If you get a set which is a subset of A complement, there mu2 will associate 0 mass. So that is the idea. Okay, so this is what is known as mutual singularity, and in this case, so this is the perpendicular notation symbol that we are using to denote this situation. So what are examples? Now whatever we have mentioned earlier in note 2, so we had mentioned two measures, nu plus and nu minus. So let's just go back. So what we said was that you look at this general measurable function f, which is given to be integrable, and look at its positive part and negative part. So there you focus on nu plus and nu minus. Okay, so now observe this, we had mentioned that nu plus assigns 0 mass to such sets and nu minus assigns 0 mass to subsets, and we can always ignore the set where the function, the given function f, takes 0 values. So that anyway you can ignore, because that's where there will be no contribution of the integration of f. Okay, f takes 0 value there. Anyway, if you wish, you can include that set to any of these sets where f plus is positive or f minus is positive. Either way, you get these sets, two distinct sets, where on one side nu plus assigns 0 mass, on another side nu minus assigns 0 mass. So therefore, with this observation and this definition, putting them together, you will write this, that nu plus and nu minus are mutually singular. Now let us see a more explicit example of mutually singular measures. So consider these two measures on the real line. The first one being the Dirac measure supported at the point 0. The other one is the Lebesgue measure. Consider this set capital A, which is the non-zero part of the real line. Okay, the complement of the singleton set 0. Here what do we get? We get delta 0 assigns 0 mass to this set, but on the complement of A, lambda assigns 0 mass, because lambda, the Lebesgue measure, assigns 0 mass to all singleton sets. Okay, so therefore as per definition, we have split the whole real line into two parts, A and A complement. On one part, Dirac 0, that assigns 0 mass. On another part, the other measure, Lebesgue measure, assigns 0 mass. So as per definition, the Dirac measure supported at 0 and the Lebesgue measure are mutually singular. But you can expect now that you can extend this example to involve any arbitrary Dirac measure and say that for any such Dirac measure, it will be mutually singular with the Lebesgue measure. Alright, but then more generally, remember that a discrete random variable has the law which is a convex linear combination of Dirac measures. Okay, So what you can now try to claim that if mu is such a law, then you can try to show that mu is mutually singular with respect to the Lebesgue measure. Okay. So that is the idea, that you can extend the class of examples for mutual singularity with respect to the Lebesgue measure. Okay. So originally you had Dirac measures, but we are now observing that convex linear combinations we will also do, but convex linear combinations of Dirac measures are nothing but laws for discrete random variables. Okay, you can try to work out this exercise. Great. Now in these above examples, what we have actually done is that for these explicit examples, we have used this null set with respect to the Lebesgue measure, right? Now recall from earlier discussion in week 5 in note 22 that there is an example of an uncountable set A with 0 mass, okay, and we had called such an example to be a Cantor set. So this is a very specific example of a set which is uncountable and has Lebesgue measure 0. So this is a very specific set. Now if you have any probability measure mu such that it assigns full mass to this set, then what will happen is that it will assign 0 mass to the complement, right? If mu is a probability measure and if it assigns full mass to the set A, then on the complement of it you will assign 0 mass, and therefore you now get this exact observation that for such a probability measure you will get that mu is mutually singular with the Lebesgue measure. Okay, so this is a somewhat of an extension of the type of mutual singularity that you have already observed. Alright. In particular, there are examples of probability measures which assigns full mass to the Cantor set, but its distribution function f subscript mu is continuous. So we are not going into the details. If you are interested, please refer to pages 13 and 14 and page 31 from this book by Kai-Lai Chung. The book title is A Course in Probability Theory. This is the 3rd edition of this book published by Academic Press. We are not going to go into the details. It involves many technical constructions. But there is a opposite type of a structure involving measures. This is something called absolute continuity of measures. So again, start with two measures and we are going to compare them in some aspect. So these two measures are defined on the measurable space omega script f. Say that mu2 is absolutely continuous with respect to mu1, which we denote by this symbol, mu2 absolutely continuous with respect to mu1 if mu1 null sets are also mu2 null sets. So what do I mean? That if you get any null set capital A for mu1 and try to check its size under mu2, that must also be 0. So any kind of an impossible event with respect to the first measure mu1 must be impossible under the second measure. Okay, so by impossible event we mean null sets, sets with or events with probability 0. Okay, alright. So here we are comparing two measures now. Okay, great. So let us try to understand what does this concept actually imply. So to do this, there are these very simple exercises. So continue with this mu and nu as in note 1 earlier. So what are this mu and nu? So let's go back to this note 1. So in note 1, we looked at this proposition from week 6, which said that for non-negative measurable functions, if you integrate them against these various sets, you get a measure, right? So that was this construction. So remember this choice of mu and nu. Okay, so here what we now claim is that there is some such a relation between this new measure and the original measure mu. Okay, so that is the concept that is being discussed here. So we are claiming in this exercise, part 1 of it, that the new measure is absolutely continuous with respect to the original measure mu. Check this. Now again, in note 2, what did we do? We took a general measurable function but mu integrable. In this case, what happened was that we split it into positive parts and negative parts and correspondingly defined this set functions nu plus and nu minus, right? and these also turned out to be finite measures provided the original function f was mu integrable. Now in this case again you can try to show that both these measures nu plus and nu minus both are absolutely continuous with respect to the original measure mu. Okay, so these are very explicit examples of absolute continuity of measures. And now you shall ask, how does absolute continuity and mutual singularity relate? Okay, so to do this there is this very simple exercise once more. Please try to work at it. So choose three measures mu1, mu2 and mu3 defined on the same measurable space. If it happens that mu2 is absolutely continuous with respect to mu1 and mu1 is singular, mutually singular to mu3, then you can claim that mu2 and mu3 are mutually singular. So that is the first statement. The second statement says that if mu2 is absolutely continuous with respect to mu1 and mu3 is absolutely continuous with respect to mu2, then if you combine them together you can claim that mu3 is also absolutely continuous with respect to mu1. So again here you are just comparing the null sets. So please check this exercise. Alright, and the final statement says forget about mu3, look at mu1 and mu2. If it so happens that mu2 is absolutely continuous as well as mutually singular with respect to mu1, then what you can try to show is that mu2, that measure, assigns 0 mass to all the sets. So this is the 0 measure. Okay, so this you can try to check. Okay, so this is what is connecting the mutual singularity and absolute continuity of measures. So these are certain important structural properties, and in the next theorem we are going to use these structural properties to discuss a very important decomposition result for measures. So we are not going to state the proof, we are just going to state the result. Now recall from earlier that in week 2 we had mentioned that we can add measures and get examples of measures. In particular we had used such structures to compute expectations of discrete random variables by saying that the law of a discrete random variable is basically a convex linear combination of certain Dirac masses. Okay, so this is a more general structure than that. Here we are adding up measures. Okay, so this theorem is known as the Lebesgue decomposition theorem. So take two measures mu and nu. Suppose they are sigma finite. Okay, so both of them are defined on the same measurable space and they are sigma finite. Now provided these two measures, what you can do is that you can find out measures nu1 and nu2 such that nu, the second measure, has a decomposition like nu1 plus nu2. So you can add them up, you can split it up like this, and the measure nu1 is mutually singular with respect to mu and measure nu2 is absolutely continuous with respect to mu. Okay, so there are these two parts. So one part is absolutely continuous, another part is mutually singular with respect to the first measure mu. Okay, moreover this decomposition is also unique in the following sense. If you can split the measure nu into two parts, let's say nu1 tilde plus nu2 tilde, such that nu1 tilde is mutually singular with respect to mu and nu2 tilde is absolutely continuous with respect to mu, then you can show that nu1 is nu1 tilde and nu2 is nu2 tilde. So this decomposition of choices of nu1 and nu2 are fixed. Okay, so given these two measures mu and nu, you can split the second measure according to the information coming from the first measure. So that is the Lebesgue decomposition theorem. Alright, but then how do you apply it? So our interests are involving probability measures. So let's work in d dimensions. So this results also applies to the one dimensional case by choosing dimension d equal to 1. Alright, so what do you do? So choose a probability measure nu. Alright, now by this Lebesgue decomposition theorem, you can split this measure nu in two parts, nu1 and nu2, such that the first part is mutually singular with respect to the Lebesgue measure in d dimension, and the second part is absolutely continuous with respect to the Lebesgue measure. So remember, probability measures are finite measures, and in particular they are sigma finite. Lebesgue measure we have already seen to be sigma finite. Okay, so this is where we are applying the Lebesgue decomposition theorem and splitting up a given probability measure in terms of the information coming from the Lebesgue measure. Okay, so we know a lot of information about the structural properties of the Lebesgue measure, and we would like to use that information in analyzing the probability measure nu. So that is the idea here. Okay, all right. Now you can now ask, can you say something more about this absolute continuity? So for mutual singularity, you don't expect to say anything more given the information about the Lebesgue measure, right? So if you go back to this, so nu1 is mutually singular. Now Lebesgue measure will associate zero mass to that set where nu1 is associating possibly non-negative values, right? Possibly non-trivial values. So there lambda, the Lebesgue measure, is not going to give you any information because Lebesgue measure is associating zero mass there. So you cannot say anything about this. But can you say anything about in the absolute continuous part of it? Okay, so that is this theorem, the next theorem. So this is going to characterize all measures which are absolutely continuous with respect to a given sigma finite measure. Okay, now we have mentioned earlier about this examples in exercise 2. So in exercise 2, what we essentially said was that if you are given a measure mu and if you integrate functions, non-negative measurable functions, you are going to get certain measures. Okay, now these are some examples at hand. Now we would like to say, are there any other examples of absolute continuous measures with respect to mu? Okay, so that's what we are trying to understand. And the next result says that these are all the things. Okay, so this is known as the Radon-Nikodym theorem, and again we are just going to state it, we don't go into the proof. So this is again stated for the sigma finite measures case. So again take two measures on the same measurable space such that the second measure is absolutely continuous with respect to the first one. Now the statement says that there exists a non-negative measurable function f such that the second measure can be written as an integration involving the functions f with respect to the first measure. Okay, so you can figure out such a function small f which is non-negative and measurable. So therefore we are saying that given this measure mu, which is the first measure, if you ask what are all the absolute continuous measures nu, you will immediately say that those which are given by such a expression or such a structure as an integration over some appropriate non-negative measurable function f. Okay, so all you have to do is to vary this set A and you are going to get back the size of the sets under the new measure. Alright. Moreover, you can say something more about this representation, that this function small f is unique in this following sense. What is this idea? Is that if you can write it as an integration of g d mu over a set A, okay, so if you can write it that way for another such function which is also non-negative and measurable, then it can be shown that f is equal to g almost everywhere with respect to the first measure mu. Okay, so outside a mu null set, possibly these two functions may not agree, but overall almost everywhere these two functions match. Okay, so that is the uniqueness of this function small f. So here, given these two measures, if the second measure is absolutely continuous with respect to the first one, you can write down such a structural property. So that is the statement of this theorem. Now with this theorem at hand, we now make this definition. So call this function, this almost everywhere unique function that you have obtained, as the Radon-Nikodym derivative or Radon-Nikodym density of this second measure nu with respect to the first measure mu, and you are going to denote this by d nu over d mu. Okay, so this is the idea, that given this second measure nu, which is absolutely continuous with respect to the first measure mu, you can get this function f, which is mu almost everywhere unique, and you are going to call it the Radon-Nikodym derivative or Radon-Nikodym density of nu with respect to mu, and you are going to write in symbols this. Okay, so let us try to understand what this Radon-Nikodym density is all about. So choose three sigma finite measures mu, nu and gamma on the same measurable space, and suppose you start with that setup of the Radon-Nikodym theorem that the second measure nu is absolutely continuous with respect to the first measure mu. Then what you can do is that for Borel measurable functions, call them h. If you want to integrate it with respect to the second measure nu, all you have to do is to multiply the function h by the Radon-Nikodym density and integrate that multiplied function, which is now measurable, with respect to the first measure mu. Okay, and this equality will hold if the integrals exist. That is the important statement that is coming out. So if you want to integrate a Borel measurable function with respect to the second measure, all you have to do is to go back to the first measure, multiply the function h by the appropriate density function. If you do that, all you have to do is to compute it in terms of the original measure mu. So how do you show this? So here is a hint for this exercise, that you try to verify this equality when h is some indicator function. Okay, and then go to simple functions and use the standard procedure of proving such equalities between integrations. Okay, but first try to do it for an indicator function. Now we have taken this third measure gamma, which we have not used so far. So what is the use of this? So if it so happens that gamma is absolutely continuous with respect to the second measure nu, then gamma is also absolutely continuous with respect to mu. Great. In this case, by the Radon-Nikodym theorem, you will get density functions of gamma with respect to mu, and we are saying that it can be split as a product of the derivative of gamma with respect to nu and multiplied by derivative of nu with respect to the measure mu. Okay, so that is the statement here. Again, please try to check this. This will follow from the uniqueness of the density function. We had started off with assuming that nu is absolutely continuous with respect to mu, but if it also happens the other way, that two measures are absolutely continuous with respect to each other, okay, if it so happens, then you can try to show that there is a relation between the density functions of mu with respect to nu and nu with respect to mu, so that they are exactly reciprocal of each other. Please try to check this. Alright. Now as soon as we have this Radon-Nikodym theorem and Radon-Nikodym densities, we are now going to apply it to probability measures on RD. So again, start with a probability measure, call it nu, on RD together with the Borel sigma field. So that is the measurable space. So suppose it happens that this probability measure is absolutely continuous with respect to the Lebesgue measure on these d dimensions. Okay. Now again, what we are trying to do is to use the information that is already captured in the Lebesgue measure. So if it can happen, if you can do that, then you get this Radon-Nikodym derivative or density function for this probability measure with respect to the Lebesgue measure, and this Radon-Nikodym derivative or density function that you get is called the probability density function, or PDF in short, of the probability measure nu. Okay, so if nu is absolutely continuous with respect to the Lebesgue measure, you get the derivative Radon-Nikodym derivative or Radon-Nikodym density function, and that you are going to refer to as the probability density function. Okay, so this gives you existence of the probability density functions for probability measures absolutely continuous with respect to the Lebesgue measures. Alright, so in this setup, if it so happens that you are going to get some function small f as the PDF of this probability measure nu, then observe that this function small f is non-negative and measurable. So that is as part of the statement in the Radon-Nikodym theorem, And moreover, you can talk about probability of events or sets of Borel sets capital A as an integration of this function, that is this density function, right, with respect to the Lebesgue measure. That is as per the structural property of the Radon-Nikodym theorem. But if you choose the set to be the whole of Rd, what happens? You are going to get back the nu of Rd, but nu is a probability measure, so therefore the total value is 1. So therefore all you are saying that this non-negative measurable function f integrates to 1. Okay, so this is an integrable function with respect to the Lebesgue measure. So this is already non-negative and you have shown its integration is finite. So therefore this turns out to be integrable with respect to the Lebesgue measure in this d-dimensional case. But continue with this notations a bit more. You are also going to make this identification with the distribution function. So what do? Choose a point x with components x1 up to xd and look at this set capital A, which is a d-fold product of such kind of intervals, that on the ith component you are going to take the interval minus infinity to xi closed. Okay, so take a look at such an interval. So then what happens? You are going to get the distribution function by looking at size of this product of intervals, right? So the size of this product of intervals under the measure nu is given by integration of the function over that set. So that is as per the structural property given by the Radon-Nikodym theorem. And here you are doing the integration with respect to the Lebesgue measure in this d-dimensional case. But then remember, in the discussion involving the Lebesgue measures and Lebesgue integrations in connection with Riemann integrations, we have seen that in one dimensional case Riemann integrations, if it exists, it will match with the Lebesgue integration. Now in higher dimensions, what will happen is that you are going to get this iterated integrals as Riemann integrations. So if you can make sense of these integrations as Riemann integrations by the similar logic, by similar arguments, you can also get back the same integration in terms of the Lebesgue measure. So that is this equality that is being used here. But more generally, since the Lebesgue integration is extension of d-dimensional Riemann integrations or d-dimensional such iterated integrals, then all you are going to say is that using the same notational structure that was introduced in one dimensions, that you are going to use the same notations for the integrations with respect to the Lebesgue measures also, just for the convenience of notations. So you are going to write this equality. So even if the original function f is not Riemann integrable, you just say that Lebesgue integration is nothing but some kind of an extension of Riemann integration. So you may be able to integrate more functions. So you are going to use the same notations for notational convenience. So that is why we are going to write down these iterated integrals as the expression for the distribution function of the probability measure nu. Okay, so this is now your familiar expression of the distribution functions and its connection to probability density functions. Now in the next lecture we are going to talk about random variables and random vectors corresponding to these various types of probability measures. So remember, earlier what we had discussed discrete random variables coming from discrete distribution functions which connected to probability measures which were convex combinations of Dirac masses. But we have now said that convex combinations of Dirac masses are mutually singular with respect to the Lebesgue measure. Alright, but we have also discussed this type of probability measures which are absolutely continuous with respect to the Lebesgue measure. So now corresponding to every probability measure you can construct random variables. So now what we are going to see are these different types of random variables corresponding to these probability measures which are absolutely continuous with respect to the Lebesgue measure. And we are also going to see random variables which are of different structures which are not falling in the structure of discrete random variables or the absolutely continuous case. It is going to follow a different kind of a structure. that will be connected to the type of examples that we mentioned under Cantor set, that we have such probability measures where you get the distribution function is continuous. So it does not have any jumps, so you cannot categorize as discrete random variables. So there will be these three types of random variables corresponding to these three types of probability measures, which are classified according to its relation with respect to the Lebesgue measure. We are going to continue this discussion in the next lecture.